Okay, so you should see a red dot. Okay, and this is physics with calculus, right? Make sure you are in the right class. So this is the textbook here recommended by the department, and it's a very nice textbook, but I don't use mastering physics. So if money, for example, is an issue, you don't need to buy it from school, but I highly recommend that you buy it online, for example, so you can buy it at Thrift Book. They have this book. Even if you get an older edition, it's fine. But especially if you are in engineering, you need to get the book because have so much time with you. We don't have a TA. So as we go through the chapters, it's very important, especially if you are electrical engineering, for example, that you go over the chapters and that you do the solve problem. If you do get the book with the school, then it's great because they do have tutorials included in the book that you get on your Canvas. And some of you get grants, right? So you can get the textbook for little money, so it's worth it. Otherwise, I don't require it. You should buy it. I like even older edition or used one. Is that clear? So I'm not using Mastering Physics because I design my own assignment based on the lectures. Okay, so let's start with the grading scheme. So I try to post one assignment per week, maybe two, mostly just one. And it's 18% of your final grade, and you have two trials. So for the first trial, 2 attempts. First attempt, you really have to do it on your own, and you have to use your notes and your brain. And you can work with friends. Study groups is great. Don't cheat, because then you have a second attempt, and then I have in my share folders, I have tutorials to help you, and everyone knows how to use ChatGPT, sadly, nowadays. But wait for the second attempt, right? The first attempt, especially if you want to be an engineer or if you want to take the MCAT, you have to do it on your own. Okay, if you need an extension, you can ask me for an extension. I rather you ask for an extension than just copy, because you can always get the answers nowadays, which is very sad. Okay, so that will be for the assignment. And then you have 3 tests in person on paper. So you have 20 multiple choices. Okay, you have to come to class. Each one is 20%, so altogether it's 60% of your final grade. Okay, including the final. And don't miss it, because for each test here I have a practice exam that I will post in Canvas, and in my share folder, which is in Dropbox, you have a practice, right? So I show you exactly what to expect for the test, but I cannot do that for the makeup. So if you have to miss the test, if you have a good excuse, it's not going to look like the practice exam that I have in my folder. So it will be more challenging. So I highly recommend that you don't miss the test. Okay, there is no makeup. If there is a makeup, it won't be the same as the practice exam that I have in Canvas, and I have a video in my Dropbox as well. Is that clear? Okay, so no makeup. Makeup are very annoying. You will have to go to my office hours at the most inconvenient time. So please don't miss the test. And the final, after the final, I'm gone. So make sure not to miss the final. This is my last semester, by the way. So I don't care if you complain. So don't miss it. Okay, make sure you're here. And then you have a test. I call that test number 3, but it's really an assignment, and it's going to be at home. Okay, I will open a very large window for you to take it, and it's mostly to boost your grade, and that will be 10% of your final grade. Okay, so it will be like a test online. Open a big window. You're going to have plenty of time to do it, and so that will be 10%. And then every lecture, you're going to have a pop quiz that will open at 11. 11 a.m., right? And you will have a window to do it. So this pop quiz will be based on the previous lecture. So for example, on Thursday, you're going to have a pop quiz that will open at 11 a.m. So make sure you have access to Canvas. The idea of those pop quizzes is first, you cannot focus that well for more than 1 hour. It's been shown, brain thing. And then second, it's for you to have some collaborative learning, to make new connections. So it's open discussion, it's open notes. Okay, it's really for you to understand what you didn't understand. So it will be mostly conceptual, and you can talk to each other and make new friends because, as everyone knows, connection, connection, connection. Right? So pop quizzes. So if you miss one, if you miss a pop quiz, then you can make it up, but only the next class, right? After the class. Because after the class is my office hours, so I can reopen the pop quiz for you. So you cannot have a makeup at home. If you have to miss the class, then you can take the pop quiz because it open at 11 a.m. Okay, so I don't do I cannot see if you are in class or at home. There are too many students anyway. So that will be 12% of your grade starting on Thursday. Is that clear? Again, it's open notes. Yes. I open it like for 30 minutes. So I open at 11, the class finish at 11:10, but I give more time for those who are entitled to more time or for everyone. But then it will close. Okay? It's mostly conceptual questions. It's mostly the idea is for you to meet new people, to talk to each other. Okay, connection is very important. So anyway, attendance is 5%, so you want to take attendance when you come in class. Now, if you add everything up, you get to 105, not 100, which means that everyone gets like if you get everything right, instead of having 100 for the final grade, you will have 105, which means that everyone gets 5 point bonus. It's included. But there is a trade-off because there is no free lunch, right? As you all know, the trade-off is if you miss a class, for whatever reason, you will be marked absent. I'm not going to scroll back because I have 100 students and change absent to present. So if you miss 1, 2, or 3 classes, it's fine because of those bonus. But don't ask me to change, even though you have a very good excuse. You went to the, I don't know, you dog something, ate your homework or something like this. So no excuse, including the Jewish holiday, for example. So you will be marked absent, right? But you have 5 point bonus, so it's a trade-off. Is that clear? Okay, and these are the tentative exams dates: test 1, test 2, test 3. The final we don't know yet. For some reason didn't post it yet. Okay, but it will be the final week. I don't drop anything. Okay, questions so far? Good. And I record the class, right? So if you miss a class for whatever reason, you can always watch the lecture online as long as I didn't forget to record it. So let's look at Canvas now. So this, I rely a lot on Canvas. So here, okay, you have the link to my Dropbox. So you don't need an account with Dropbox. So I do that because it's a lot of stuff, and Canvas get upset when I try to post the PDF. They complain, you know, that there is not enough. What do they call that? Canvas accessibility report. I get in trouble there. So it was easier to have everything in Dropbox. I don't get monetized by Dropbox or anything. So here, if you click there, you're gonna have all my slides. So we want to start by downloading this unit 1.1 because we're gonna start with static electricity, electrostatics, right? And then here, so that was before ChatGPT, but staying there. For each assignment, you have a tutorial, right? So if you click here, I have a tutorial for all the assignments, most of them. So if you need help, I go step by step. Sometimes ChatGPT may a lot of mistakes, by the way. Okay, you should not rely on it too much. So tutorials here, and here I have the practice exam. For each exam I have made a tutorial, and so that will be 1, 2, and the practice, the final. But again, if you miss a test, if you have a good experience, I can give you a makeup, but the makeup will have nothing to do with this, the practice exams. So try not to miss a test, right? It will have to do with the topic, of course, but not the practice exam, because it takes me so much time. It's very, very challenging to make a practice exam. And then you have some stuff you can watch. So physics 2 relies a lot on vectors, okay, vector analysis. So if you need to review, and if you are taking if you're an engineer, and you will have to take calculus 3 or 4, I forgot the name, but you will have to understand vectors. So if you didn't take physics with me, or if you forgot, I highly recommend, since you are not too overwhelmed, this is the first week, to look back at vectors part 1, vectors part 2. So this is really the basics, fundamentals, right? You really have to understand vectors. And then a little bit more advanced here, you can watch Vector Dot. So this is a very nice YouTube channel. And this one too. But this one, he has free videos. Only a few of them are free. Otherwise, you have to pay. He has a tutorial. He's a tutor. I mean, he has videos online, and this one is about the cross product. So dot product, cross product are two ways you can multiply vectors. So this one, the dot product, is also called a scalar product, and it's going to give you a scalar with no direction. This one is a cross product, and that will give you another vector. Okay, so these are really good tutorials, and I highly recommend that you watch them. Are you with me? You survived? Good. Okay, and that takes you to my YouTube channel here. So I try to record the lectures and I upload them here. So if you are late, if you have to be late because you come from MMC, it's fine. And you can watch the video online. That was from last semester, no, last year. So I will post this video here in that YouTube channel. I don't have enough subscribers to be monetized, sadly. I will never get enough subscribers. It's really for my students. Okay. Because of the MMC thing, the buses, it's very hard to catch them. Okay, and here you have the equation sheets. So what you can do is to download them, and then you can use them for the test. Okay, you can bring those equation sheets to the test, only those. Okay, I have two kinds here, and this is for math, derivative and integral. Okay, so those you can print out, and I highly recommend that you do it now, so then you keep it in a folder and you can use it in class, for example. Okay. Okay, you get in trouble here, or because they complain, oh, your PDF is not accessible enough, blah, blah, blah. And then if you have too much trouble here, then you get a bad grade, and then someone from the school email you. So that's why I have to use Dropbox. So anyway, that's for the story. Here, I have a lot of resources for you. So nowadays, you can have free textbook online. So this is a big one, OpenStax. It's very famous. And another free textbook. And this one is algebra based. So if you take the MCAT, for example, it's good. And then blah blah blah, this is good too, and this is a good YouTube channel. This is great, this is amazing. So that was done by a professor, and it's good for engineering as well. So it's covering every topics in physics, right? And it has also simulation, so electricity, magnetism. We're going to start, for example, with electric charge, and it has all those explanations, and you have also like small simulation. Okay, this is super nice. You see, you have those things like this, you can practice. So this is great. This is amazing. And then if you want to, if you are a physics major, for example, I highly recommend to watch those videos by Professor Walter Levin. It's a little bit more challenging than this class, but he's an amazing professor. He was an amazing professor. I mean, he's still alive, but he doesn't teach anymore. He got in trouble. Uh, so not taking attention. Let's go back to here. Medical physics here, also interesting. So if you want to have something that summarizes everything nicely, okay, I highly recommend that you get, and it's $3, like very cheap. It's called by Princeton Review, Cracking the AP Physics B and C, but you want the old edition, like from the 2000s, because now they changed the AP and it's more conceptual. It doesn't go deep enough in the math, but this one is very nice. Get the old edition, the 2000 edition, right? Princeton Review is the best. By the way, if you are taking the MCAT, Princeton Review is also very nice. Okay, so what else? And then here you have the first unit, and sometimes I post videos to watch, and you have one assignment per week. And then that will be the first pop quiz, maybe on Thursday at 11 a.m. Okay? Did I review everything? Any questions? Okay. And for the office hours, it's just after this class. I go to my office, which is AC 1387, somewhere in the hallway, should be in the hallway. But otherwise, you can ask me after the class. Before the class, it's hard. I think I have to run before the class. Possibly after this class is better. Any questions? So we're going to start with electrostatics, right? So statics means not moving. So that means we're going to study the behavior of charges that are not moving, electrons, but they are not moving. So you are not applying a voltage to make them move. So that will be electrostatics. So I'm going to introduce the class. And as introducing the class, as I'm going to introduce the class, I'm going to go through history, a little bit of history. So static electricity, the first time it was documented, not understood, but documented. That was done by the Greek philosopher. I forgot his name, but the Greek have noticed that if you take, for example, a piece of amber, so amber, it's like from the trees, right? The fossil resin from the tree. In the movie Jurassic Park, they get a piece of amber, and inside they find a bug, and they get the DNA, and they make a giant mosquito or something like this. So this is amber. And what they did notice is that if you take amber, right? I have someone gave me a gift. It was a student. Carlota from Mexico. You see, I have a piece of amber here. So they notice that if you take a piece of amber and you rub it against wool, so at the time they have clothes made of wool, then you can pick up some little pieces of straw, right? And you can even make sparks. And they didn't understand what's going on. Now we know that what's going on, if you take a piece of amber and you take, for example, wool, so here I have silk, right? And you rub them together, what's going to happen, because you are doing work, so remember physics 1, doing work, right? You are transferring energy. What's happening is that there is a transfer of electrons. Okay, you are transferring electrons from one material to the other one. So in that case, silk loves electrons. So electrons are transferring from the amber to the silk. So the amber becomes charged, and because it becomes charged, you can make little sparks, or you can pick up little pieces. So at the time it was straw. I don't know if they had paper at the time, but if you have little piece of paper and you rub it, let's see if it works. You see? I don't know if you can see here. See, I pick up the little piece of paper. So that's because it's called polarization. But what is showing you is that the amber is charged. It has lost electrons. So for something to be charged, it has to lose electrons or to gain electrons. Right? So thank you, Carlotta. So, and because people, like especially women at the time, in Greek civilization, they could not go outside, they could not do politics, they could not do nothing. So they had something to entertain themselves. They will wear jewels made of amber and rub it. So they will rub it against fur, for example, and they will shock frogs, right? Make spark because electrons, they always want to jump to something bigger, and the frogs will jumps like in despair and in misery. So that was fun to do because they were bored. So by the way, I forgot to tell you, if you want extra credit, you can make videos of an experiment that you do, like something hands-on, right? That it has to do with the topics. So maybe if you want to get a piece of amber and see if you can make a frog jump, I don't know, you can try that. But anything, anything. Um, the points that you will get depends how good is your experiment, right? If you don't want to do it, don't do it, because last semester everyone did it and it gave me a lot of work watching all those videos. But if you need extra credit, if you don't need, don't do it. Only if you need extra credits, right? So anyway, interestingly, electron means amber in Greek. So that's what it comes from. It comes from the word amber. Okay, is that clear? So the rubbing thing. Uh, so then in the 17th century, they start to understand those experiments, right? They were doing those experiments where the same idea. You have two insulators. They has to be insulated. So what's an insulator? It's a material that with electrons that they cannot move. Okay, they cannot go to the conduction band. They are not free to move. They are attached. They are very faithful to their nuclei. Okay, they don't want to mess around. But if you do some rubbing, two insulators rubbed against each other, then the electron will be transferred but not move. Okay, so if I rub them together, the electrons will be here, but they cannot move because it's not a conductor. So they started to understand that in the 17th century. So they started to build what we called electrostatic generator, static generator. So what they do, they take two insulator. So here you have wood and this is rubber, right? They will crank, so doing work. So because of the energy, there is a transfer of electrons. So one will become negatively charged, the other one will be positively charged, and the electron will stay there. And the electrons always get upset because they don't like to be isolated, right? The only thing the electrons want to do, for example, is to go to the ground. They want to go back to the ground, right? So here, electrons are very upset to be there. And if you bring something here which is made of metal, you're going to make a spark. So they were able to produce spark. So these are called electrostatics machine. Okay, electrostatic machine. It was really the beginning of 17th century. So in the salon, for example, in France and in Europe, they were quite bored. If you were a noble person, for example, you don't have to work, you get bored. So you have those very sophisticated salons, and they started to have fun with that. Okay, so you have an electrostatic machine rubbing against his feet. He is a conductor, so the electrons, they don't just stay there, they're going to spread over because they can do that if it's a conductor, and you can make a spark and go and shock everyone. Okay, there is an experiment that you can do with the Van Graaf generator, and you make a chain, and then the last student get the spark. which is very fun. But here you have another one. Okay, so electrostatic machine, the best example will be what we call a Van Graaff generator. Okay, it's the most famous one. So this is called a Van Graaff generator. So it was developed in the 1930s at MIT. I think they have the copyright, right? From 1933 by a professor at MIT. It's a genius, very, very smart machine. So in that one is cranked. So you have to use your hand. The other one, you can have a little motor to make it spin. So here you have a belt. It's made of rubber. And here you have a drum, which is another insulator. And it starts to spin. Okay, so the rubber here, the belt, because of the spinning here, you're going to separate electrons, right? So you're going to pick up some electrons. Okay, there is a transfer of charge. The electrons will be brought up to this dome here. That dome is made of metal, so it's a conductor. So once electrons are brought to the dome, because there is a connection, there is a little connection, there is a wire inside, those electrons, they say, oh, a conductor. So now they're going to start spreading out. Okay, they spread out as much as they can. You're going to start building charges, okay, up to a point. Okay, so this is like a capacitor. It has a capacity to hold charges up to a point, because if you try too much, then it's going to discharge. Okay, so you can hold charges here, and then you can make a spark, or you can shock people, or you can have experiments done. So that's what they did in the 1930s. They built a huge one, and they made particle accelerators, because doing this, when you are building up the charges, you're going to have a very high voltage. And if you have a high voltage, you have high pressure to push charges. So you can build a particle accelerator. Okay, this is not dangerous, because even though the voltage is very high, like 1000 volts, what do you think when you touch it, right? There will be electricity flowing into you, but the electricity flowing will be very small. The current will be very small. So it's not so much the voltage that kills, it's the current. So even though the voltage is very high, you're going to touch it, it's going to be very unpleasant, but it's okay. So I don't know if I have a slide. Van Graaff generator. You see, if you go to Boston, where MIT is, they are displaying those old Van Graaff generator, and they have all kind of experiment with it, and they are still doing experiments, right? In biology, in labs, they are still using them. So this is an electrostatic machine. Okay, so I have a mini one, because I cannot get anything here. When I want to get an experiment, it's very hard. So I bought this one. So this is fun. It's called a flying stick. It's for kids, but it's like electrostatic machine, because inside here you have a motor, right? And you have a belt. You have a belt, and it's picking up electrons, and this is becoming charged. And I can show you that. So here you have, I don't know if it's gonna work, right? This is an electroscope. So electroscope, it's metal, and this is movable. So if you charge it, what's going to happen to this? It's going to move, right? Because if everything is negative, if the electrons get here, it's a conductor. So they're going to move as far as they can from each other, because they hate each other, and negative repel, and it's going to move. And this device was used to measure charges before, in the 19th century, right? So if I do that, do you see how it moves? See that? So it's very hard to hold the charge because we are in Florida and it's very humid. But today is not so bad because it's holding it. And if it's very humid, it's leaking out. But if I touch it, I'm going to ground it, pyong, and all the charges goes from my body into the ground. Okay? So when you rub, you separate the charges. Okay? So experiment, there are so many experiments for extra credit you can do in electrostatic. So this one is a famous one. You can check if your lungs are working well too. So this is the conductor or insulator? Insulator. And what it does, it's rubber. So rubber doesn't like electrons. It's going to give up the electrons, right? So if I do that with my hair, can you see my hair standing up? Yeah. So because electrons are transferred from the balloon to my hair. So my hair becomes negative, so we repel each other. Now those electrons, they're not going to travel anywhere. They stay where you put them. Okay, because it's an insulator. Now it's very hard to show. See, it's not enough to move this one. So I can try to do it with this. You see it move. You see it? I don't have 3 hands. That's my problem. Well, I can try. And you see it moves a little bit, right? But you see how the electrons on an insulator, they don't want to move. So even though it's moving, but they don't want to travel, right? They stay blue. There's a fun experiment to do with your cats, right? You take all those little balloons, water balloon, and you rub them, and then it's going to stick to your cats, and your cats go crazy. It's you can try. I don't know if I have the cats. Have a dog. Can try. If you have that little dog, right, or your cat, you rub it with a balloon and see what's going to happen. So anyway, here it's something fun. You see, this is neutral, this is neutral, this is neutral. This is an insulator, this is an insulator, this is insulator. So let's review some physics. I'm doing work, so I'm rubbing. So the balloon will become negative. The balloon likes negative. Okay, likes electron. Sometimes I forgot. Sometimes it's hard. Well, there is a hierarchy. You know, some likes electrons, some don't. So wool and rubber, the rubber takes the electrons. So there is a transfer of electrons. But can you see the electrons are not moving? Okay, if you put electrons on the conductor, they will move. Here they can't. They are glued. They will be stuck. Depending if the weather is humid or not, it will stay or it will leak out. Positive and negative attract. But what's interesting is that it's going to stick on the wall. And that's very interesting because this is called polarization. Polarization, very important in the material science, in engineering. Polarization, it means those electrons, they cannot move. Okay? They cannot move far away, like they cooled in the inductor, but the molecule here can be polarized. So the electron, the cloud, the electronic cloud will move a tiny bit. So this is polarization. So one side will become positive, the other side will become negative. That's why it's going to stick. Even though it's neutral, this is not neutral anymore. It has lost electrons, so it's positive. This is negative, this is neutral. But this is called polarization. That's why you can pick up a little piece of paper because the paper becomes polarized. Very important in chemistry because a lot of, like with water is polarized. You have a plus and you have a minus. Minus goes to the oxygen, plus goes to the hydrogen. So even though it's neutral, it's polarized because oxygen loves electrons. That's why you talk about oxidative stress and things like this, because oxygen wants to steal electrons from proteins, for example. So this is called polarization. Okay. Now, if you have a conductor, so this is a conductor, and he's going to rub his foot here, but the electrons are not going to stay there like they stay on the balloon. Okay, this is a conductor because it has some electrolytes inside, and so the electrons are going to move inside, but they will try to stay on the outside. So that's a principle that we will learn. When electrons are transferred to a conductor, it won't stay inside. It always goes outside, not inside, outside. Okay, so if it goes here, see, the electrons are moving, and little by little, they're going to settle on the outside as far as they can from each other. And they get upset because they want to go back to ground. So that's how you get a spark, right? This is a very good one because they call that Travolta, staying alive. Okay. So let's go back to history. So I'm introducing a lot of concepts and we will revisit them. So 18th century, still, that's when they built the first capacitor. Capacitors, if you are taking electronics or electric circuit, you learn about them. So many things you can do with them. You can filter. You can get rid of high frequency. You can get rid of low frequency. You can use it as a timing machine or timing device. You can use it to store charges. You can use it in a computer as like a small battery. Right, so capacitors, any electric circuit will have capacitors. And to understand how it works, you think about a defibrillator. So defibrillator is a capacitor. So you have two electrodes. You connect that to a power supply. One electrode is positive, the other electrode is negative, right? Positive and negative get very upset because they want to get together, right? So you put that across the heart, and there is a discharge because plus wants to go with minus. But in the meantime, you are storing charges, you are storing energy. Okay, and then all that energy is going to be used because the heart is an electrical device, and then you have the discharge, and the current will make your hopefully waking up the dead. Right, the heart will start pumping again. Okay, so anything in the body is electrical in nature. Biologists don't want you to know that because they don't like physics, but everything in the body is electrical in nature. The heart is an electrical device. The way neurons work is electrical. Everything is electrical. So anyway, 18th century, you have, I cannot say the name right, from Holland, Peter van Munchenbroek, right, made the first capacitor, and we call it the Leyden jar because he was from Leiden, and I guess no one can say his name, so they called the capacitor, after the city here. And what he did, you see the same idea. He has a static machine, electrostatic machine. So you have two things rubbing against each other. You are separating the charge. The electrons here gonna see, oh, this is a conductor. Let's go there. So they move. This is metal. They move there, and they're gonna stay in the chain. This is a metallic chain. So this is minus, 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 minus. And when you touch it, you are connected to the ground. And the ground is like a reservoir of charges, plus and minus. Even though it's a minus that will move, let's say it's minus and plus. So you touch it, and all of a sudden your hand will become positively charged because they see electrons and they are totally turned on. Okay, they go crazy. Ooh, this is minus and this is plus. So they want to get together, but they can't because here you have water, which is like called a dielectric. Okay, they can't get together, so they get very upset. So this is plus, this is minus. But if you close a circuit, you're going to be shocked, right? A huge spark. So this is called a capacitor, right? So that was the first one built. It's a way to store charges. One is negative, this one will be positive. You disconnect from the ground and you can hold charges for a very long time, and then you can close a circuit and make a spark. So you can use that as a battery. Okay, you can use that as a battery. You can use that to store charges. So in a computer, laptop, it goes 0110011. So you can use capacitors for memory, 1110 charge, not charge. Now they use also transistors. Okay, is that clear? So the first Leyden jar was a big breakthrough in electricity, even though they didn't know about the electrons yet, right? All they understood is that you can store charges and then kill people, because if you have too much of it, can be very unpleasant. So that idea was picked up by Franklin Roosevelt. No, did I say it? Yeah, not Franklin Roosevelt, Benjamin Franklin, sorry. And 1817, just after the Leyden jar. So he started to do experiment. You see, he has a Leyden jar there. He did very dangerous experiment that you don't want to do. So he had a kite, and it was very stormy. So when it's stormy, the atmosphere is filled with static electricity. And here you have a string, which is a conductor. Thread here was a conductor, and that so the conductor here goes to a key, and the key goes to his body, and he goes to the ground. So all the electrons that were picked up because of the rubbing, right, will go through the thread into his body. And he got shocked, but he didn't die. And somebody else tried the experiment and died. Okay, so don't do that experiment. And be very careful in stormy weather. It's not very safe. Like they did that. What they did is kind of dangerous here. You see all the static electricity, because this is very stormy, and you can see the hair, and they were able to make sparks. Right? Now this is dangerous, okay, because you are connected to the ground, so they can jump to you. Okay, so Benjamin Franklin, he's the one who understood that electricity is made of moving charges. Okay, something is moving. So he understood that you have two kinds, the plus, and they didn't, he's the one who called it plus and minus, but two kinds of fluids, one that moving, one that doesn't move. So he decided to call negative and positive. So that was before the electrons, right? The electrons was not discovered yet, right? So he had 50% to get it right, 50% to get it wrong, and he got it wrong because he said that the positive charges move, and we know it's really the electron that move. So if I ask you conceptual question, which one move, is the electrons, the negative charges. But he had 50%. Okay, didn't know. But we love Benjamin Franklin so much because at the time we didn't have that many scientists, right? Most of them came from Europe. So we still today, we stick to that convention, and we're going to pretend that electricity is made of positive charges moving and flowing. But actually, it's really the electron. But we're going to pretend it's not. So by convention, the electric current going from plus to minus will be positive moving. We're going to pretend that. Okay, so that was a big breakthrough. And then 1780, by mistake, the first battery was built. So if you want to build a battery, you need two kinds of metals, right? So here is an experiment, very easy to do. It's the lemon or the potato batteries. Maybe You did that in high school or in middle school. So you take, for example, a potato, it could be a lemon, anything with some kind of acid inside, acidic. You take two metals, right? Zinc, for example, and copper, just an example. And the zinc is going to give away its electron and it's going to be picked up here by the hydrogen, positive hydrogen, because it's a pH, acidic pH, so you have H plus, it's going to pick up the electron. So you're going to have electricity flowing, you have yourself a battery. But he didn't know that, okay? He didn't know that the one who built the first one, he was experimenting with frogs, and I'm sure you learned that in chemistry. I don't know what's the deal with frogs, why he liked to torture frogs that much, but that's what he did. Okay, it's just by chance. And he started to connect here to play with that, and the frogs will move even though it was dead. So what he didn't know is because you have two kinds of metals, right? And electricity was flowing from one metal to the other one. And when we have electricity, that the muscle can move. He didn't understand what's going on. He thought that anything like animals or human will have some kind of fluid inside, electric fluid, and that will explain life. He didn't know that. He didn't know what really was happening, but you see, he had two kinds of metal here, so that's why you have electricity. That's a battery. That was the first battery. Isn't that interesting? I will not accept this experiment, okay? This is no. You're not going to torture frogs. Don't do that. It's already terrible to have to do dissection. I mean, no. Okay. His name was Luigi Galvani. Obviously, he was Italian. And Betty didn't really understand what was going on. But then electricity started to be very interesting to people. They thought, okay, maybe it's the source of life. Okay, so that's how Mary Shelley she wrote her book. You know about Mary Shelley, Frankenstein, right? Frankenstein. So he get a corpse from the cemetery, and then there is electricity here, and then he comes alive. So in the real book, it's very sad because the idea of the book is that you create your own monsters, and the monster, end up killing you or ruining your life. That's happening in the book. The book is very, very dark, very famous. But then there is a very famous movie. I don't know if you know it because it's very old with Mel Brooks. It's called Frankenstein Jr., which is hilarious. It's not PC, but it's still hilarious. It's very, very funny because he get the corpse and then he get a brain, and instead of getting a smart brain, he gets not a very smart brain. So it's all movies about it. It's not PC to our standards today, but it's very famous. So anyway, the one who really understood what was going on, right, how to make a battery, is Alessandro Volta. Okay, he was Italian too, and he understood that to make a battery, okay, to produce electricity in a continuous way, not like in a capacitor where you send a spark, is to have two metals. So you have two metals. In between, you need some kind of juice, like electrolytes. Like in a battery today in your car, it's the same idea here. A 12-volt battery, that's what you have in your car. Okay, and you see you have layers. So each cell is 2 volts. You have 6 of them, that will be 12 volt. So that's what he did. See, in France, because by the way, he was a count. He was knighted by Napoleon. Napoleon was French, obviously, and so he called this a pile. Pile in French means a battery, right? Because a pile means a pile. It's a pile. Pile of two kinds. One unit is two kinds of metals, and you have some juice in between, and you add up the voltage. So if one cell is 1 volt, you have 1, 2, 3, 4, 5, 6 volts, and you get to 6 volt. So big breakthrough, because now they know how to produce electricity. Okay, and for the story, he was Italian, moved to France, and he loved Napoleon. Luigi Galvani didn't like Napoleon. So if you go to Italy, you visit some places and you see that some people didn't like Napoleon at all. They hated Napoleon because they said he had bad manner. Right? He was not very polite. He didn't know how to behave. So anyway, he did not like Napoleon. So because Napoleon was in charge of Italy, he got in trouble. And for some reason, Volta didn't like him. So he lost his professorship and he lost his pension. And I think he died in penniless. Sorry, not penny at the time, but he in poverty. So that's for the story of Napoleon. See, so for example, if you open like a golf cart, okay, you have 6 volt, and you have 6 of them in series. What do you get? 36 volt, right? 6 times 6, right? It's a picture taken in North Miami. I don't know what's going on there. They must have races. They steal golf cart and then they race and they end up in the canal, which is not nice for the environment. But I thought it was interesting, so I took a picture inside. Okay, any questions so far? Okay, so I'm just introducing the class and the concept that we go over, and it's nice to connect to history a little bit. So then came Humphrey Davy. So that we are in England. I think he was in charge of the what's it called? The the Royal Institute of London. So anyway, Humphrey Davy, what he did, so you must know him from chemistry. What he did, he used the Volta battery and he got the idea to connect them in series. So because he connected them in series, you increase the voltage. First of all, you can produce a huge spark, and he used that in the streets, right? You can have a street lamp, but also he used that in chemistry, and he came up with electrolysis. So electrolysis is when you put 2 electrodes in some kind of solution, and thanks to that, he was able, the first one, to isolate potassium, sodium, calcium, magnesium, and so forth and so on. So he's the father of electrochemistry. I know some of you usually are always very good with chemistry, right? He was the first one to use electrolysis. So you apply a voltage, you have 2 electrodes, right? You apply a voltage. That energy is used to separate compounds and to isolate elements. So I'm sure you did that experiment in chemistry. You have water, you have plus electrode, minus electrode connected to a battery. On one electrode, you're going to have hydrogen, and the other electrode, you're going to have oxygen. So you're going to separate hydrogen from oxygen, and then you can use hydrogen as a fuel, but it doesn't work very well. It's not very efficient because you have to put energy in to start the process. Is that clear? Okay, someone did the experiment with that. Like there is this experiment. You have hydrogen, oxygen, and you can show that oxygen is, I think it's oxygen which is flammable. But you can do that experiment. So anyway, he's the first one to do that. He was also very famous because he was an amazing public speaker, and he would get high, not on cocaine, but on laughing gas. You know about the laughing gas? Nitrous nitrous oxide, right? And you can still use it today at the dentist, right? Like I'm very sensitive, so if you're very sensitive, you can get that, but it make you hilarious, right? So anyway, he was very famous to get high on that before the presentation, and he will have party with his friends where they will all get high. Apparently, it has a comeback. Like some kids, they get high on it. It's not good for the lungs, right? So anyway, apparently he didn't die from that. He died from I don't know what I think heart attack. I thought he died. He was not very very old. So anyway, okay. Any question? Laughing gas. Okay, so here we are in the 19th century. Okay, so first battery, 19th century is full of breakthrough and experiment. That takes us to Faraday, Michael Faraday. So he's my favorite physicist, Faraday, Michael Faraday, because he was the son of a blacksmith. So at the time in England, if you are not wealthy, you cannot go to school. There is no school. Okay, if you are wealthy, you can be homeschooled. If you are not wealthy, you cannot go to school. So they will use kids to work. I don't know if you know about Charles Dickens. It tells you how miserable life was at the Victorian era. I'm not sure it's better today in England, but at the time it was horrific. So they will use kids to clean the chimney, for example. So when you watch Mary Poppins, for example, it looks fun, but it was not fun, right? They use little kids to go down the chimney and they will die very young, and they will use kids to go in the sewage. So terrible. But he was lucky. He got to work in a bookstore, right? Binding books. So it was before glue, they will bind books together, and he learned on his own. So he didn't go to school, he didn't go to college. Nevertheless, we owe electricity to him. If we have electricity today, it's thanks to him because he figured it out how to do it. So he was a very good experimentalist, and he was the student of Humphrey Davy. Okay, so they had some fight because, of course, he started to work for him in the lab, and then he became jealous, and then they get along. So anyway, in the 19th century, they made that big experiment kind of by chance, and it was when they started to play with the battery, so you have electricity flowing, right? It's called the Oersted experiment, and there was a compass on the table, and the compass moved. What do you think it means? If a compass moves, it means you have what? Magnetic field, very good. So it means, surprisingly, that electricity can produce a magnetic field. Wow. Until then, they thought they were two separate topics, right? You have the magnet, the magnetic field, and you have electricity. And now they found a connection. So using this, Michael Faraday built the first motor, because if you have electricity behaving like a magnet, electricity can push and pull and push and pull and push and pull, and that will make the first motor. And then the question is, I'm asking you, if electricity can produce a magnetic field, then what's the next question? Yeah, so is it possible that magnetic field can produce electricity? It's not that obvious, right? It took 1810 to 1831, 20 years to understand how to do it, and this is how we have electricity today. Okay, because he understood that if you have a coil, closed coil here, so that could be a power plant connected to a load, that could be your house, and you move this, so it's in a power plant, you have a generator, it's moving inside a magnetic field. That's how we produce electricity today. And it didn't understand how to use it at the time, but it was a big breakthrough. And apparently he said, the king of the time said, okay, that's cute, it makes light, and what's the idea? And he said, one day you will be able to tax it. And it's true, right? When you pay for electricity, it's not so much a kilowatt hour. It's only, in Florida, it's only 15 cents, right? It's the membership that you have to pay and the taxes, right? So anyway, so big breakthrough here, right? You survived? Any questions? Okay. It's just an introduction, and it's also good for chemistry So then, 19th century, the end of 19th century, it was the beginning of modern physics, right? So non-stop discoveries up to Einstein and then quantum physics. So crazy time. So this is J.J. Thomson, end of 19th century in England, I think in Cambridge, and he discovered the electrons. Finally, they start to understand how electricity works. It's moving electrons. So the way he did that, so at the time they built what we call the vacuum tube, okay, cathode ray, it's called, okay, and inside that cathode ray you have a special gas, and when you're gonna send, here you have two electrodes. So you have a beam of electrons. He didn't know about electrons yet, but you can visualize this beam of electrons in a cathode ray tube, and he was able to deflect it using a magnet and using an electric field. But you don't need to know the details. You can dig deeper into that. My point is that he discovered the electrons. Okay, so that was a big breakthrough. So they didn't know how the nucleus was built. So he came up with what we call the plum pudding model. So this is something disgusting that they eat in England. You know, plum pudding, I don't know if you know, and they have this gelatin thing that we go around. I don't know how they can eat that. England, food from England, in my opinion, okay, it's not very good. So anyway, he called that the plum pudding model because he thought that you had some kind of positive dough, and included inside you have electrons, like plums, like pieces of plum. That was his model. Okay, and they were starting to understand how it works. So let's see. See, you see one here. So you're going to apply a very high voltage, positive, negative. The voltage here is so high that the filament, let's say this is negative, the filament here gets so hot that electrons can escape. Okay, they have enough energy to escape. Electrons are not happy. They want to go to the positive here. Okay, so negative going to the positive, and you can visualize a beam of electron. So this is called a vacuum tube, or CRT. And why it was a big deal? Because using this, then they built the first computers, right? With IBM. The first computers use those things because you can control electricity on, off, on, off, on, off. So that was the first digital computers, right? So the first computers, they had those huge things inside. So this is called a cathode ray tube for those going into chemistry. And that's what you have in the old TV. Okay, my grandmother, when I was a kid, so that's very, 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 very long time ago. Okay, we didn't have flat TV. We had those TV here. So maybe you find those in your grandmother house, something like this. I don't know. These are antiques, right? It's just a vacuum tube, and then you have a beam of electrons sweeping out and making the screen. Right? That's how it worked. The oscilloscope, the old ones, use CRT as well. Okay, are you still with me? Okay, so that was 19th century, the end, beginning of 19th century, the Millikan experiment. I'm not going to show it to you; that will be too much. But you can Google it, and they did an experiment, and they were able to find the charge of an electron. and the mass of an electron. Before, he had only the ratio between the mass and the charge. Now they had the mass of an electron and the charge. And then his student, the student of J.J. Thomson, Ernest Rutherford, he came up with a different model. After doing a very famous experiment, which is called the gold leaf experiment, another experiment. So at the time, everything was experiments, right? So he did another experiment, came up with this model. So now you have the nucleus inside made of protons, positive charges, right? And you have electron on the outside on energy level. I'm sure you're familiar with that. Okay, energy level. So this is called the Rutherford model. And then 1932, Chadwick doing an experiment, because at the time, it was at the time of Marie Curie. They started to understand radiation, radioactivity, nuclear energy. So they started to experiment with radioactivity. And using an experiment, using neutrons, they not they were using neutrons, they were using alpha particles, but he discovered neutrons 1932. So this is relevant to what we're going to learn this semester, because now they have the right model, almost. That was before quantum physics. Now we know that electrons, they are in a cloud, right? But it's the idea. You have the nucleus and the neutrons, and you have the electrons. And in a metal like copper, only the electrons, the valence electron, can be moved if you apply a voltage. Not insulator, only conductor. Okay, so you see here you have a metal like copper, and those electrons, the outmost electrons, they are free to move, and they do move, right? They are not very faithful to their nuclei. Just because there is some temperature, they move and they wiggle and they shake around, but it's very random. If you apply a voltage, they will start to drift in the same direction, and you have electricity. If you have an insulator, you have a big gap. And so if you apply a voltage to this balloon, electrons will not be willing to move. And then in the 50s, by chance, at the Bell Laboratory, they built the first transistor. Transistors are made with semiconductors. So it just happened by chance. Someone, 1956, at the Bell Laboratory, New Jersey, he was trying to make a hearing aid, like something to help people hearing better. And then it was picked up by people understanding electronics, and they made the first transistors. So transistors, if you are in electronics, it's just like a gate. Okay, so it means you apply a voltage, and then the gate open, or it can be closed. So it's like a switch. It's an electronic switch. So with this transistor, you can go 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. So it's digital computers. You could do the same thing with IBM, with the vacuum tube, because you go 1, 0, 1, 1, flowing, not flowing, 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 but you see it's very bulky. With the transistors, it was a revolution. So that led to the Silicon Valley, right? All those transistors. So anyway, how semiconductor work? It has a small gap here. So it's not that hard for electrons to jump to the conduction band. It's not that hard. You just need a little boost. You boost, ping, ping, and then it's going to jump. So that way you can control electricity. So you can go 1, 0, 1, 1, 0, 0, 1. Is that clear? It's just an introduction, but you have to be very careful when you work with semiconductor. Everything has to be without dust. You have to make waffle here of silicon, and then you make those little chips. So anyway, so we have come a long way. So that's that's how they did it before the laptop and the tablet, right? You have to go up a ladder. And then that was the old computers, first IBM. So the first computer were as big as this wall, right? Huge. And they were using vacuum tubes, right? A cathode ray tube. And then you didn't have keyboard and you didn't have screen. If you are interested, like apparently those kids, Gen Z, very interested in the, it's called retrofuturism, like old stuff. So maybe you are interested in that. This is called a punch cards, IBM punch card, very famous. So that will be your keyboard. Okay, so that will be the input. So 0011011001. Put that in the computer, processing, and then you have the output. Right? A lot of women were in charge of those cards because very detail oriented. You have to be very focused, I guess. So anyway, so we go from here to the digital age. Any question? I don't know if I should start. Okay. Okay, if you have any question, let me know. Okay, don't hesitate. It's good to practice public speaking skills, especially because you are in engineering, so usually people tend to be shy, so it's good. You can speak out, no problem. You can ask questions, nobody will say anything. Certainly not me. Okay, so on Thursday, 11 a.m., we're gonna have a pop quiz, right? Based off what I've said, but you can help each other, you can talk to each other, it's open notes. Okay, so just an introduction here, the atom. So you have the nucleus, and then you have electrons in clouds, electronic clouds, right? So because after that came quantum physics, and quantum physics says that electron is not like a particle, it's more like a wave, it's a particle wave. So you don't know exactly where the electron is, it's like a probability to find the electron. But you learn about orbitals in chemistry. So anyway, my point is here. So this is the place I used to work at. So this is the Bronx. Here, you see, this is a basketball over there. If you have your nucleus here, so if the nucleus will be the size of a basketball, the electron will be that far. Okay, so there is a huge distance between the nucleus and the first electron. Huge empty space. So it means this is empty space here. But I cannot see it because I have a very bad resolution. I'm blind, first of all. But even if you're not blind like me, you cannot see it because your eyes have very bad resolution. But this is empty. So I should be able to go through the wall. Right? Why? Why I cannot go through the wall? Yeah. What kind of force? Between what and what? Yeah, very good, right? What's your name? Your name? Huh? Leo. Tell me your name when you participate so I will remember you at the end of the semester. I did remember some of you at the end of the semester, and you did see that I have boosted your grade. So anyway, he's right. Your hand is made of electrons. This is made of electrons. So you think you are touching it, you are not touching it. It's just repelling each other. Okay. Now, quantum physics says that if you keep pushing long enough, there is called a tunnel, something called a tunnel effect. You should be able to go through the wall. But you have to push like a million years. So I guess I will be dead, pushing all my life. But it's not impossible. So if the size of an atom is 10 to the negative 10, the nucleus is 10 to the negative 15. 15 for hydrogen, for example, 15 minus 10 is 5. So that will be 100,000. Okay, so that distance here is 100,000 times the size of the nucleus. So if I have something very small in my hand, right, that will be the nucleus. The electron will be going around BBC. Okay, that's how much emptiness there is. Okay, so that's a nucleus again. That will be the mass of a proton, the mass of a neutron inside the nucleus, and this is the mass of an electron. You see that proton and neutron, they have about the same mass, agree? Which one has more mass? The proton or the neutron? The neutron, right? So that means more mass means more energy. So a neutron can easily turn into a proton during a nuclear reaction. This is called the beta decay. It's willing, it will do it. But the opposite, a neutron into a proton, a proton into a neutron can happen, but you have to push it, you have to force it, right? So in the sun, so I don't know if you read the news, but they talk about fusion a lot nowadays. It's fusion and AI and fusion. So anyway, they try to do fusion. That's what's happening in the sun. In the sun, you have enough pressure, enough temperature to convince proton to turn into a neutron. So if you have 4 protons, hydrogen, um, hydrogen, and 2 protons turn into neutrons. So now you have 2 protons and 2 neutrons. What do you get? 2 protons and 2 neutrons. One proton is hydrogen, 2 proton is helium. So in the sun, turns hydrogen into helium, that's fusion, huge amount of energy. This is not the atomic bomb, the hydrogen bomb. That's the idea of the hydrogen bomb. So anyway, let's go back to this, and you see that the electron has less mass. So if I ask you conceptual question, it has about 2,000 times less mass. So that's why in chemistry, you only talk about the atomic mass. It's only the number of protons, because the electron is about 2,000 times less mass. So we forget about that mass, right? When we talk about atomic mass, it's just protons and neutrons. Okay, is that clear? So the electron has a charge. Yes. So fusion, in summary, you have, so first of all, you don't have nucleus because, you know, it's like a plasma. So you have 4 protons, like hydrogen, but without electron. Electrons gone because it's very hot. So you have 4 hydrogen, which is 4 proton, and they are pushed together because of high temperature and high pressure, and they have a crisis, identity crisis. So proton becomes a neutron, this proton becomes a neutron, and when they combine together, no, so two, sorry. So this one becomes a neutron, this one becomes a neutron, and when they combine together, that's going to give you helium. So 2 protons, 2 neutrons is going to give you helium. Right, so it's just a proton turning into a neutron. And how that can happen is because inside here you have subparticles come quark, and they change. Like from up they go down, and they change their identity. So a proton becomes a neutron, and then they combine together and give you helium. So fusion is just hydrogen turning into helium. There's huge amount of energy, and this is called the hydrogen bomb. The nuclear weapon, nuclear weapon, right? It's hydrogen bomb. Hydrogen bomb is like more than the atomic bomb. Does that answer your question? I don't know if there is something more simple. See, here you have two hydrogen plus and plus. One hydrogen become a proton, a neutron, right? One hydrogen, so it's one proton become a neutron, and now you have deuterium, and then deuterium combined again with hydrogen, and at the end you're gonna have helium. So it goes more complicated, but basically it's when a neutron, a proton becomes a neutron. Proton can turn into a neutron. Oh, here, this is much better. Okay, four protons. Okay, two protons have an identity crisis, turns into a neutron. They combine together, and you have helium plus a huge amount of energy. So it just summarizes. And why? Because inside you have quark. See, inside a proton and inside a neutron, you have three subparticles, and they are called quark. So when a proton becomes a neutron, what happened? Do you see what happened between here and there? Up quark didn't change. What changed? This one changed, right? It was up, and all of a sudden you say, no, I'm tired to be up, my back hurts, let's go down. So now you have a neutron. It's very advanced. Okay, it's just a tangent. Okay. So anyway, the this is the elementary charge. Okay, E. The notation is E, and that will be the charge of one electron, except it's going to be negative, and it's also the charge of one proton. Okay, so charge is a property of matter, the same way that mass is a property of matter. So mass is in kilogram, the charge will be in coulomb. So a proton and the electron, they have the same charge. So when a nucleus, an atom, sorry, is neutral, you're going to have the same number of protons and same number of electrons. Yes? Yes, I'm losing you, so we're going to stop here. We have a pop quiz on Thursday. If you have any question, let me know. So I stop record.